All right, hello everyone. So this is the second lecture of 1301. In the last lecture, we started with some review on kinematics. And as you're going to see in this module, we're going to build up from one lecture to another, more or less. We're going to use the previous knowledge in order to produce new knowledge. So today we're going to focus on 3D kinematics. I wrote the title here, down here, because this is the most painful place where you have to be on your knees when you're writing it. 3D kinematics. So we're going to move from 1D. We're going to make a more general observation of what happens when we move from 1D kinematics as last time to 3D kinematics. We're going to talk about vectors, dot and cross products. And we're going to discuss a very important concept in physics, which is decomposition of vectors. So let's start from where we stopped last time. We discussed velocity and acceleration. We talked about the gravity as an acceleration, and I showed you a photo of the tennis ball being strobed by light, where you see the distance becomes larger and larger. If we want to write the equations that would describe the position and the kinematics also, position, velocity, and acceleration of the object in a general way, then we can do the following. We say x, so the position, you see that? We say x equals to some initial position of the object, which we can say as C1 is a constant, plus C2, another constant, times t, that will give us the position, the new position in time, right? C1 plus C2 times t plus C3 times t squared. Now we know that to get the velocity, all we need to do is to take the first derivative. So the velocity would be C2 plus 2 times C3t. And the acceleration, which is the second derivative of position in time, or the first derivative of the velocity in time, that would give 2c3. We talk about constant accelerations. Now we can start also talk physics, not only mathematics. Remember when I told you about the units, how important they are. I know that C1 here has to have units of distance, meters, maybe feet, whatever, but it's a unit of length, because x is the position, right? X has units of length. C2 times t has also to be units of length, and C3 times t squared has to be units of length. I know that t is time, so C2 times t has to have units of length divided by time. So when I multiply that by t, I get units of length. Now I know that for some of you this might be obvious, because you know C2 has to be velocity, right? It's meter per second times the time that will give you the position. But we're going to start from the basics, and then it's very important to develop step by step. And we want to think about of any results that we get at the end of the lecture. Okay, so I can now say that x1 here, C1, I can take as some x0, being the initial position. So this is the initial position. And C2 here, you see it appears here and there, has to be velocity. So C2 is some V0, which is the initial velocity, right? Velocity. I have here this term 2c3 because we deal with the constant acceleration that would be the acceleration. So c3 I can define as half some acceleration a. Yeah, it's not the same a here. You could write. I could have written this a something else, but we're going to use a. So I'm going to write here a. The half here is just for convenience. So I don't have to carry that to everywhere when I talk about acceleration or when I talk about velocities. But it would appear here, as you see. And also, by the way, do you see the full screen? Because I see a different screen here. Do you see my full screen or do you see? Okay. Okay, all right, that's okay, yeah, all right, great. So C1, C2, and C3, they are the constants, and these can be either positive, negative, or equal to 0. Okay, these are real numbers. Now, when we talk about gravity, and normally when we talk about acceleration, not always, we consider gravity. If we consider gravity, A would be G in terms of magnitude, and that is equal to 9.1 meters per second squared. Why meters per second squared? Because the acceleration has to have units of meters per second squared. Ah, all right, yeah, thanks. 9.81 meters per second squared. Thanks for the correction. Many times we just will take it as 10. It varies from one place to another on the Earth, on the specific location you're talking about. Later on, we will go away from the surface of the Earth, and then we cannot consider the acceleration being constant. That comes later on. So it's 9.81. You can take it as 9.8. If you're solving, unless if you're told, you can assume it's 10. As long as you state my G is 10 meters per second squared, that's completely fine. Okay. So now we move to 3D kinematics. We talked about velocities, we talked about speed. Now, if you want to define quantities in physics, sometimes you can just say one number and that completely defines the quantity that you're talking about. For example, if I say the temperature in this room is 20 degrees, then you know everything about the temperature in this room, it's 20 degrees. I can say the pressure outside, today the weather is not so good, later on we're gonna link that with pressure going down or pressure going up with the weather. And then you can say also give a number for the pressure, and it's one single number and you know everything about the pressure in that place. But there are quantities in physics that it's not enough that you say the number. For example, what we saw last time, when we talked about the velocity, we've seen that it has a direction. We've seen that the plus 30 meters per second velocity of an object is larger than the minus 100 meters per second, because it's a definition, because positive is larger than negative. but the magnitude of the velocity is larger in the case of the minus 100 meters per second. So what is plus or minus? It has to do with the definition that we put for the axis, for the increasing value of the axis that you put. So if my increasing value of the axis, of x-axis in that direction, then the plus 30 would be there, the minus 100 means it's in that direction. So for me to be able to tell you about this velocity, I have to tell you two things. I have to tell you the magnitude, so like 100, that's the magnitude, 100 meters per second, and the direction, I point to the direction. I can use an arrow. And I say it's in that direction. It's a 1D problem, so it can be either in that direction or in that direction. Let's assume that I say this is the plus x direction. You're going to use mostly that as a plus x direction. You can use any other direction. If this is the plus x direction, and I want to tell you minus 100 meters per second, then I would say, okay, the magnitude is 100 meters per second, and the direction is in the opposite direction of my increasing value of x. So you can use arrows to describe vectors. Now, I'm sure that you talked a lot about vectors, but I'm not sure that you have ever seen one. And, well, in different circumstances, you would be able even to hold it and look at it, and it will look back at you. It's important to look at vectors sometimes, because if you look from the pointy part towards you, what you would see is a circle with a dot. And that is going to be our way of saying that the vector is going outside of the wall. So it stands, the tail is inside the wall, and it goes all the way towards you. Now, you could also look at the back. This is an old vector, but normally you would see an X if you look at the back of the vector. So if the vector going, the back of the vector is towards you, what you would see is something like this. So this is our way to say that the vector goes into the wall. This one is out of the wall, and this one into the wall. We use vectors intuitively, right? Even as kids, and not only as kids, you would point to something, right? And if you're following something and you see the shooting star that's too fast, but if you see an airplane, for example, and you want to tell someone it's going that way, and then you're showing where it's going, this is called the position vector. We're going to use this a lot. So it starts from you, from this frame of reference where things are fixed. They don't have to be fixed, right? I can also walk. It just makes things more complicated. And I can still follow that point in the sky, the airplane, for example. But it starts from you, and it points directly as if it was a straight line touching that object which is moving. This is exactly our X here. It doesn't have to be in 1D. Now it can be in 3D, right? And it would always point and follow wherever the object is going. So if you take the derivative of that position vector, that would tell you the velocity of the instantaneous velocity of the object. If you take the next derivative, it will tell you the acceleration of the object. Okay, so now you've made the object. Let's see what we can do with the vector. So let's see what we can do with the vector. The first thing that I want to do is try and sum that vector. But before I do that, I'm going to do the following. I'm gonna stand up on a table. All right. Imagine that I'm standing up on the table. I can show you here. And I want to go in a straight line. Okay. So here I am standing on the table at this point, which I call it, this is the origin. I start with that point, we call it O, and I want to move from O to point P. This is point P. So I move in a straight line. I just walk on a table in a straight line. That's fine. And you're sitting here, and what you see is that I'm going from that point to that point. I see myself, well, I see that point actually getting closer and closer to me. But we can discuss this later on. But from your frame of reference, from where you're sitting, you would see me going from point O to point P. Now, I'm going to do the same thing, but now while I'm walking from point O to point P, one of the students decides to, for whatever reason, to move the table from this point to here. I'm walking in a straight line. For you, you'll no longer see me walking from point O to point P, because now the student is also moving the table. So just to put this clearly, the table now is just being translated, okay? Translated, and I'm emphasizing that because we have no rotation. So it goes from here to here. I'll put it now in the red line. So for me, I started at this point on the table, and I ended up at some point here. But what you see now is that I would end up at that point, which I would call S. I will end up at that point, but what you would see me doing is actually moving from O to S. And now the question, how can we understand what's happening here? And I'll do the following. So I have one vector here, OP, and I have another vector, which is here, which is PS. This vector is exactly this vector here. I'm going to put it like that. So it goes from P to S. In terms of the length, right? It doesn't go from P to S, but in terms of the length, it's the same length. So we have OP. We start with OP. And we add up PS, and that gives OS. What you see is just OS. So how do we sum vector? There are two ways to do that. Probably you already know, but I'm gonna teach you both ways. I'm gonna show the both ways at least. So one way, which is called the head-tail technique. Imagine that you have a vector A. Is this still inside? Yes. And a vector B. Vector A has this magnitude. The length tells me the magnitude. Vector B has this magnitude. The length of vector B tells me the magnitude. And this is exactly the direction. So right now you see my vectors are in some plane, which is in the volve. They don't have to be. Okay, so we have A and B. What I do is I take vector A. So this is the tail and this is the head. I put the tail of vector B on the head of vector A. This is vector B. Anyone wants to say something, or if not, please mute yourselves. Otherwise, the picture might jump from one place to another. Okay, so we have vector A, and this is vector B. And what you do, you connect the tail of vector A with the head of vector B. We can call this vector C. This is A plus B equals C. Now the other way of doing it, which is called the parallelogram technique, is the same concept really. So you have vector A and you have vector B, so you put the tail on the tail, and then you make this parallelogram. That's why you get the name. And if you do that, you get this thing, right? And what you do now is connect this point with that point. And again, that would be C. So A plus B gives C. What you note from here is that A plus B also equals to B plus A. Okay. So we have now added two vectors together, and one can ask, what happens if a vector is negative? Is it possible to have a vector being negative? Yes. Remember, the vector has a direction, right? This is the direction from the tail to the head. The negative would be exactly the opposite. That's all. So this equals minus this. So now we can write negative vectors vectors A equals minus A, which means now you can subtract also vectors, because if you have now A minus B, so subtraction. If you have A minus B equals C, then if this is A and this is B, then A minus B is nothing but A plus minus B, which means I can replace B by minus B. This would be the minus B. And we know how to do that. We know how to add vectors. We put this on the tail of one on the head of the other, and then we connect. So the result is, to be consistent, let's do it. Blue is C. Okay, that's the easy part. The other way to see this is that A minus B equals C. You can write it as C plus B equals A, and you see this here. C, or B plus C, right? B plus C equals A. That's exactly the head-tail technique. the tail of C is the head of B, and A is from the tail of the first to the head of the second. All right. Now, unlike the beginning, I was speaking about some quantities that it's enough to describe them by a magnitude like pressure and like temperature. These are called scalars. A scalar is, if I have, for example, 2 degrees plus 3 degrees, that gives me 5 degrees. You add the 2, it gives you exactly one answer. With vectors, is a little bit more complicated. If I want to add 2 velocities together, that depends on the not only the magnitude but also the direction. For example, if you have a magnitude, I'm going to put it in absolute values. So a magnitude of 2, right? If I know that that one of the vectors has a magnitude of 2, right? But I don't know, it could be +2 or -2. And the other one has a magnitude of 3. Let's do it in a more accurate way. So the first one has a magnitude of 2, and the second one has a magnitude of 3. If I add them together, yes, I can get 5. That is in the case that A is also 2 and B is also 3. This would give A plus B equals 5. We are talking one dimension now. However, if A is -2 and B is -3, the magnitude is still 2 and 3, but the summation would give, let me write this as C is -5. I could also have +2 here and a -3 there, or -2 here and a +3 there. So you already see that it's more complicated than scalars. When we add vectors together, they are different. The magnitude and the direction are important. So there are different possibilities. Okay, now we come to the probably the most important part of this lecture, which is called the decomposition of vectors. It's going to take a while, if you're not familiar with the concept, to understand why do we do this. It looks like we're complicating things. But as time passes, hopefully by the end of this lecture, I might take a few minutes from the tutorial. Hopefully by the end of this lecture, you start feeling that the decomposition actually makes life easier. The decomposition, basically, the idea behind it is very simple. Imagine that we have a Cartesian coordinate system. So we have X, Y, and Z. And I have a vector. It's in 3 dimensions now. Decompositions say, don't solve the problem with this vector being in that direction. Instead, just as we were able to sum vectors together in order to make one vector, so A plus B can be C, you can think of A plus B plus C in 3 dimensions, and that would give you one vector. It sounds like it's easier to use only one vector rather than, so you're solving one equation in a vector form rather than solving 3 equations. Why 3 equations? Because if you take that vector now, you can look at the components or projections of this vector in the X, Y, and Z directions. So in the X direction, if that is my X direction, I would have a projection in that direction. I will have a projection in this direction, and I will have a projection in this direction. This is called decomposition. We take that vector and we see the projection on the axis there. It doesn't have to be Cartesian system. Later on, we might see different systems, but right now, coordinate systems. But right now, we're going to talk explicitly about Cartesian systems. So let's start with decomposing a 3D vector in space. So I hope at least that the concept, you understand now the concept. Maybe you don't understand why we do this. You will start appreciating why we do this when you solve problems. You try to solve it with a vector, you get stuck, and then you try to solve it with the decomposition, and you see that things are actually much easier. So we have a vector in 3D space. Let me try and draw the coordinate system. Hopefully today also you will understand why, if this is the x-axis and this is the y-axis, this has to be the z-axis. It cannot be the minus z-axis. You don't have a choice in that. I'll explain later on. And it's very important. It's a common mistake, and if you do it, end of story. Everything that you do is just meaningless. So we have x, y, and z, and we have a vector. I'll try to draw it in space. I can't draw it in space, but I'm gonna try to do the following. If I take the projection first in the x-axis, so the distance okay. I'll explain all these. Okay, so this is the projection in the x-axis. I'm gonna put it very soon. In the y-axis would come here. I'm gonna use colors soon, gonna be easier to see. And then in the z-axis, it would go, let's say something like this. Okay. So my vector goes from the origin, let's call it O to P, point P. This is my vector, and this is vector A. I decompose it. Now I can look at the projection of the vector on the x-axis. On the x-axis, this is what I will see. And I'm going to call this AX. Do I need to put a sign of a vector on top of AX? No, I don't need to do that. Yes, well, no, right answer. I don't need to do that, and the reason is that it is standing on the x-axis, and it gives you the magnitude of the vector. Okay, so it's no longer a vector. It's not treated as a vector. This is the magnitude of the projection in the x-axis. In a similar way, now we have this projection here in the y-axis, and I can say this is a y. And we have the, you see, it has to go all the way. This is the length. The length is the magnitude. The magnitude of my vector here is this length. So this would be AZ. I can define now this angle here as phi. And I make use of that later on. And this angle here with the vertical axis as theta. Now, if I want to decompose this vector A, I have to say that vector A now equals what? Equals AX in the x-axis. I don't have anything that is telling me what his x-axis is. So I define a unit vector. A unit vector always has a length of 1 unit. What is the unit? It's up to you. It doesn't matter. It can be 1 meter. It can be whatever you want. It is just telling you that it's in the direction of x. The length would be ax. So the unit vector I can define as, you can define it as many ways. I'm going to write here, this is x with a hat. This is y with a hat, and z, oh, the other z. Okay. All right. So I have x, y, and z. The unit vector is always, x direction is always in the x direction. So I can write ax in the x direction, and then I write plus ay in the y direction, plus az in the z direction. Now you can say, well, big deal. What have you done? Now, if you take these three, you put them together. This is exactly what I started with. You take two vectors, you put them together using the head-tail technique. In a similar way, you can make also for the third one, and then you end up with that vector. Why complicate things? Why make out of one vector 3 components? We get to that. But remember, each component would be solved in its own direction. There would be no vectors there. Okay. What is the magnitude? So this is the projection. The magnitude of A is the square root of ax squared plus ay squared plus az squared. So we know the magnitude, and we also were able to decompose the vector into 3 components. Let's make an example. We have 3x minus 5y plus 6z. This is my vector A. The magnitude, if you want to know the magnitude of A, is the square root of 3 squared, 5 squared, and 6 squared, which is, I think, square root of 70. You can check that out. You can also find theta, cosine theta is az over that magnitude. Please verify that at home. And it should be 6 over square root of 70. The length of z is 6. The length of the component in the y direction is 5. Length is always positive. It's the direction, it's in the minus y direction. Okay, now we get to something which is a little bit more complicated, which is multiplication of vectors. We have 2 types of multiplications. One is called the dot product, and the other one is the cross product. We're going to start with the easier one, which is the dot product. Dot product. So you can write, if you want here for completion, this can be either dot product or cross product. Or you can just put dot for the dot and cross for the cross. So the dot product, which is also known as a scalar product, And the reason is that if you have two vectors and you apply a dot product, the result is a scalar result. We start with A dot B. This is just A dot B. Well, you can think about it. A has AX in the X direction, AY in the Y direction, and AZ in the Z direction. The dot product is telling you, look at that direction, and you can look at the product in that direction. So you'd have AX times BX. And then look in the Y direction, you'd have AY times BY. And then look at the Z direction, you have AZ times BZ. So AX BX plus AY BY plus AZ BZ. Note, there is no longer vectors here. These are all magnitudes. So this is a scalar product. This is one way to find it. Another way, if you have the vector here, so you have A and you have B, and if you happen to know the angle between A and B, I want you to think about it, why it is actually equivalent to what we have up there. You can write A dot B equals the magnitude of A times the magnitude of B times cosine the angle which is in between. A hint, if you look at the cosine, if you put B in the X direction, you would see that the cosine of theta is actually giving you the projection of A in the X direction, which is in the B direction, right? Think about it. So it gives you exactly what you have here. Sometimes it's more convenient to use this. Other times it's more convenient to use this. If you know the angle, you can immediately apply this and you find the product. If you know the lengths, right? Here you have to calculate the lengths, right? As we did before. If you already know the components, then you can use this following. And note that this can be, the product can be positive, can be negative, and can also be zero, right? If theta, if they are both in exactly 90 degrees, right? There is no projection of A on B. So it has to be zero in that case. Okay. You might say, how do I know how to take eta? Is it in that direction or in the other direction? In this case, the direction is not important because you have a cosine. Whether you define eta positive in that direction or define it in that direction, so whether you have, in other words, if you have plus eta or minus eta, that doesn't matter because you have a cosine. All right, I will take one little example here, but it's a very important one. If A is just the unit vector in the y direction, that's all. And B is the unit vector in the z direction. I asked you what is the product. You can type if you want in the chat, the product of A dot B. Oh, I wrote the answer. Well, anyhow, the answer is zero. We said that before because the theta in between is 90 degrees. There is no projection of one vector on the other. So think about it in terms of projection of one vector on the other. They are perpendicular to each other, right? The one is in the y direction, whatever y direction is, and the other one is in the z direction. And these are 90 degrees in between. There is no projection of the one on the other, or the projection is zero, if you want. Okay. Now we move to the more difficult product, which is the cross product. But think about it in the same sense of projection. I should keep this. The one which is the dot product, you actually want to look at the components in the direction of the vectors. So you're actually looking at these components that multiply each other in the direction. However, with the cross product, you're looking at the perpendicular ones. So what's important is the perpendicular ones. Gonna be clearer soon, hopefully. So we have now cross product. And again, there are two ways of finding the cross product. You have A cross B equals C. The first way of doing it, it's time consuming. I do recommend that you actually stick with it because it's quite safe. And if you ever played, the very first video games, like Pac-Man, or if you remember that screen that you start from one side, and if you leave the screen, you end up coming from the other side, you can use that actually here in applying the cross product. So it always reminds me of these games. What you do is the following. You look at, you write initially here, you write the unit vector, which is x, y, and z. The order is very important. I am going to even write it here in red. The order is important. A cross B is not like B cross A. A dot B is equal to B dot A, but A cross B is not like B cross A. So you need to be careful with that. If you have A cross B, the first line is always the unit vector. The second line would be the components of the first vector. So we have AX, we have AY, we have AZ. And then the components of the second vector. If I had B cross A, I would start with B first and then A second. I'm going to write the proper X here. Nothing is proper here. It's B X, B Y, and B Z. Now, what you do is the following. You always start with the diagonal, and you start from the X going in that direction. I'm going to do this in colors. See how much colors we have. So I go in this direction first. And what I do is I can write now, we have AY times BZ in the X direction. So I write AY times BZ, and that is in the X direction. I'm gonna leave space here for later on. This is in the X direction. I go to the next one. I just move this. I go now to this one. So I start from Y. Now I need to do it with just dashed. Okay. I start from here. Oops, I go out here, so I come back here. So what we have next is plus AZ times BX in the Y direction. So I have AZ times BX in the Y direction. I leave space here for later on. The third one, I'm going to make it dotted. So I always start from the top, and you always go in the same angle. So I start from here. I go back here. So now we have plus. This starts to be very painful for the knees. We have ax times by in the z direction. So we have ax times by in the z direction. We're done. We're not really done, but we have to do now the exact opposite. And that's why I left the space here. And that is in the minus direction. Minus direction means that I start with x, but instead of going in that diagonal, I go to this diagonal, but there's nothing here. So again, I start from here. I'm going to use now light green. So I start from here. So it goes to this side. This green is terrible. I'm going to use, do you see the green? I barely see it from here. I'm going to use the red, okay? So I start here. And go like that. That's now in the opposite direction, so it's in the minus x direction. We have a minus az by in the x direction. Now we do the same in the y direction. You have ax bz, the minus sign, ax bz minus the last one. You have to dot it. It's just is diagonal now. Bx ay. Bx ay. This is the vector C. And you see now that this product, cross product, gives you a vector, unlike the dot product. This used to be long to do. Now it's long and painful because of the position of the board. Okay, so we have now the vector, the cross product C. Do we actually have everything? Not really. There's one thing missing. There's one thing missing. This is a vector, right? I know the components of the vector. Do I know the direction of this vector? Yes. I know the directions because I know that this is in the x direction, this is in the y direction, this is in the z direction. All I need to do now is the head-tail technique for these three vectors, and that will give me the direction of C. So the magnitude and the direction. I know the magnitudes already. Let's look at another way of finding the cross product. Is much easier, but then you have to think of the direction. That is the harder part. It's not that hard actually, once you get used to it, if you're consistent. So the second way of doing the cross product is if you, similar to before, if you had A and B, and if you knew the angle which is between A and B, then you could write C equals A cross B, which is the magnitude of A, the magnitude of B, and I'm sure that you can guess now, it's going to be sine of theta. So before it was a cosine, and now it's sine of theta. I gave you a hint before. When it was the dot product, I mentioned that the components need to be in the same direction. That's why it's a cosine. Now it's a cross product. What's important is that they're actually perpendicular. So it is the sine which would give you that perpendicular projection of one vector on the direction of the other vector. Think about it. It's not that easy to understand from the first, even if it looks like, oh, it makes sense, think about it. You really need to have to give some thoughts in order to make sure that you actually understand this idea of projection, because later on it's going to be much more complicated with the vectors. That's going to make things much easier for you if you have that physical understanding of this product. All right. I see that I already passed the time, but as I said, I'm going to take a little bit more time from the tutorial, and after I finish, we're going to have 5 minutes break. If you want, you can agree with Berna on that, and then he's going to start with the tutorial. I have to finish this this part. It's painful, but you're going to do it one time, and that's it. How do we find the direction? How do we find the direction of this product? There's a way to find it, which is called the right-hand rule. If you heard about that, you actually not find that in many objects that we have around. But the idea is very simple. So you take your right hand. This thumb here would be the direction of your vector. So this is the head of the vector. So if you end up in that direction, it means that the vector is from you outwards. Okay? Or if we talk about the board, then the direction is from the board outward. If you end up deciding that the direction is actually like that, it means the direction is into the wall. Okay. In terms of symbols, this is going to be the X symbol, right? And this is going to be the circle with the dot. So how do we decide? Now, if this is the direction of the vector, there is a rotation. The rotation is important here. Later on, we would understand also maybe some physical problems that would link directly to rotation. Rotation is if you go from one vector to another, the rotation is dictated by these fingers. Okay, so this is the direction of the rotation. So if my hand is like that, it means I'm rotating like this. We're gonna define what is like and what is the anti-like. Okay, so if I do it like that, this would be counterclockwise. If I do it like this, yeah, this is the direction of my rotation. I never do it like that because this is the opposite direction of the rotation. The rotation is always in the direction of the fingers, like that, okay? So this would be, as you see, this is clockwise. Clockwise, in this case, is going to give me into the wall. If I do it this way, it's anti-clockwise, and it's going to give me a direction which is out of the wall. I'll do it again. This would give into the wall, and this would give out of the wall. And I never do it the other way around. Okay, you have to remember that. You have to agree on that. You always use the rotation in the direction of the fingers. Now, you might have encountered in school that they will say the rotation is right or left. This is nonsense, right? You can say right or left if you define a point and you say it's relative to which point. But if you talk about the clock or anything else, right? The rotation is either with the clock or so clockwise or anti-clockwise. Okay, so if you have the wrong concept of to the right or to the left, that doesn't work, right? You have something like this, and the rotation is like that. Don't think this is to the right because this is to the right from the top. It is to the left from the bottom. You need to think in terms of rotation. So it is clockwise, or once you use this definition that this is clockwise, you can say the rotation is into the wall. Into the wall means that actually clockwise. Okay, that's not everything. Now we need to see how we actually get this. If I have A cross B, I have to go now from this vector, from vector A to vector B. If I do that from A to B, my hand has to be in this position, from A to B. So the direction of C is into the wall. What is the, we have comments? Okay, let me explain this in this way. If you ever seen this tool, all right, most of the screws really, unless if you're a biker, you would understand that. Think about it, that there is some ways of doing it in an opposite direction. But let's concentrate on this. If I take this, I put it in my right hand. You always use your right hand. Doesn't matter if you're right-handed or left-handed. And I do it in this direction, right? I'm going to do it just faster. You see this start going inside. If I do it in the opposite direction, this will go this will go outside. This is inside, this is outside. So this into the wall, as you see, it's actually clockwise, right? So clockwise is into the wall. Counterclockwise, it's out of the wall if this is the, right? So if I want to go from A to B, then I will have to hold this in this direction, right? Because I need to start from A to B. A to B. Do it here, A to B, and it gives me into the wall. It takes time and practice. So we can put also the direction here. The direction of C is into the wall. So you see now, if I had B cross A, what would you get? That's the question. Okay, great. So if I have B cross A, I go, this might maybe easier to see. If I have B cross A, so B cross A, I start from, this is a strange A. I start from here, and I go that direction because I start from B, and I go there. So it's out of the wall. So B cross A is out of the wall. A cross B into the wall, B cross A. I can write now is minus A cross B. Okay, a little bit more. I know this is intensive, but we do it one time and then we can leave it behind us. Let me give you one example, and then let me give you one example, and then I will let all right. I will hold you 5 more minutes, because if I don't do this now, then it's going to be hard for you to try and solve the problems. We talked about the, so I'm not going to go with the example, then I will take care of the examples. The last thing I'm going to do now, remember the object. What we're interested in is not the cross products, it's not the, what we're interested in is following that object and trying to predict where it's going to go in the next step. To do that, as we said, we need to know the x, v, and a of the object. So I can write down I'm going to use this vector to actually follow my object. So my vector now is pointing at the object, and this is what I call the position vector. So it starts as vector A. I'm going to call it r of t. So this is my vector, and it's r of t. It starts pointing, touching the object, but now it's moving in time. It's no longer like that vector A. It starts as vector A, but it's changing in time now. Okay, this is my position vector. This is position vector. So now just as before, we would have something like y of t. This is the component in the y direction, but it's going to be a function of time. That's all. Az now is going to be z of t, and it's going to be x of t. So now I can write a position vector RT which is what? X of t, right, in the x direction, plus y of t in the y direction, plus z of t in the z direction. Just as before. It's just now xt, yt, and zt, they are a function of time. If I want to know now the velocity, all I need to do, and we know that already, so we were using the past knowledge from the last lecture, v of t, which is the velocity, is dr dt, and that gives what? dx dt in the x direction, plus, what is dx dt in the x direction? Is we can just write, instead of writing dx dt, I'm going to write x dot. Okay, so the x dot will tell me that it's the derivative in time. It's just going to be easier to write. Then we have dy dt. So instead of writing dy, I'll write y dot in the y direction, and then z dot in the z direction. Just makes things easier to write. And then the acceleration, now I can write as, which is d, this is dr dt. It's going to be now dv dt, so dv dt, and that gives now x dot dot in the x direction plus y dot dot in the y direction plus z dot dot in the z direction. Okay, so what we did is we took that vector, right? I can start with, I have the ball here, I threw this ball, right? And this ball now is no longer in straight line going. I can throw it, and it goes, it makes some trajectory, which is very complicated. I will be standing at some point, so it starts here, and I will be following this. So if this is my position vector, it will go like this. This is my position vector actually, right? And it's just following it everywhere. And it gives me the position. If I know the position, I can calculate the velocity, and I can calculate the acceleration. In the next lectures, we can start making use of this. When we start actually solving the problems, hopefully today you'll see some examples, then you will start appreciating this decomposition. I'm going to stop here, and you can have a few minutes break if you want, and I will give the stage to Bernard. Bernard, are you there?
Yes, thank you.
All right.
Okay, as Usama mentioned, you can take 5 minutes break. However, I will be here responding any question that you can have those 5 minutes. I've seen that a few questions are raised in the comments, for example, related to the notation of the three-dimensional vectors. I think you can use x, y, z or I, j, k. It doesn't matter as long as you're consistent. So I suggest you to stick to one of them all the time, okay? That was one of the questions. Another question is if you are gonna be told to use dot or cross products. I think further in this topic, you will see that this type of operations are related to some physical processes. So further on, you will be able to identify which tools do you need to solve physical problems, okay? So now just try to understand how to compute them and get familiar with them, okay? Another question was, why can't we just use clockwise or an anti-clockwise? Okay, I think it's pretty clear that the right hand rule, it has just one direction, and it's the direction where the fingers cross, okay? So I strongly suggest you to also get familiar with this rule, the right hand rule, okay? And you can just use one direction because you can just close the fingers in one direction, right? That's the beauty of this. Okay, let me start the video. I hope everybody can see me and see the screen. Okay, I'll give you 5 minutes. Does anybody have any question? Okay, wonderful, thank you. Okay, the right hand rule. Apparently, you're struggling with it, and that's perfectly normal because I also struggled with it at the beginning, okay? Especially if it's a new concept for you. Okay, so as you can see, you can just close your fingers in one direction, right? So we understand that. We also understand that it's the right hand rule. So you can use your right hand, okay, for this type of problems. Okay, we also understand that the cross product, because we use this on cross products, in a cross product, the order matters, okay? So A, X, B, it's not the same as B cross A, okay? We need to understand this. Do you see what I write in the whiteboard? Can you see it? Okay, wonderful. So it's not the same. And why it's not the same? Well, because of this. Let's say I have A, okay, and B. The directions where each of the vectors point are clear, okay? So what happens here? Imagine a three-dimensional space, okay? So you have X, Y, everything, okay? Three-dimensional space. We have 3 dimensions, okay? And we have those 2 vectors, okay? So if I want to compute A cross product B, I would have to close A towards B. So I take my right hand and I emulate how A would cross to B with my right hand. A crossing to B. So my thumb is pointing downwards. The solution is going to have this direction, okay? But on the other way around, if we want to compute B cross product A, B closes towards A. So I close my fingers in the same direction as B would close to A. So now I would have my finger pointing upwards. Is this clear now? There is only one way to compute this. Fair enough. I also encourage you to access YouTube and look for explanatory videos try to work this out, okay? Because if I explain it now, but you don't work it out, you will forget it. The only way to settle this knowledge in your head is to work it out, okay? Well, it would be out of the paper, but we're kind of picturing a three-dimensional space in the paper, okay? Now we are just working with two-dimensional, three-dimensional spaces, okay? Maybe further on in another subjects, in another courses years, you will have to work in more dimensions. So I strongly encourage you to try to make a picture in your mind. It would be upwards. It depends, right? It depends the plane. So for example, let's say that this is a kind of table, okay? We can imagine a table. Okay, I'm not very good with pictures, okay, but more or less you can have an idea of this table. So you see that A and B are in the table, are on the table. They belong to the plane that the table describes, okay? So B cross A would point upwards, okay? And on the other way around, if I do A cross B, I would point downwards, below the table, yeah? You're welcome. Okay, guys, so I've been suggested to spend 10 minutes trying to summarize the last lecture's concepts, okay? So I believe you worked on, okay. Yes, well, the angle was not important. I think the angle is not important. It doesn't matter the angle they describe, right? It matters for the magnitude, of course, but it doesn't matter for the direction, okay? We are working out just direction so far. The right-hand rule is just for directions. So it doesn't matter if they are very close than if they are very far, okay? It's just the way. You just want to figure out the direction, okay? Then if you want to compute the magnitude, the angle is important, okay? Yeah, exactly. Thank you, James. I think you got the concept pretty well. This is a very important concept, okay? Cross products are very important in physics. So please pay special attention to them. They're really, really important, especially in angular movements, okay? When we work on circular movements, we will go through them a lot. Okay, so as a summary for the chapter 2, the first chapter was related to units, physical quantities, and vectors. You are all smart people, so I believe that you completely dominated this topic. If you have any question, please feel free to ask it. And now I will just go through the summary of the chapter 2, which is motion along a straight line, where the most important concepts are average and instantaneous velocity, okay? So we know that if we work with average, we are gonna work with delta, capital delta. So we work with increments, okay? Okay, sorry. So we will basically, oops, time, of course. So we will basically take the final velocity, the initial velocity, we will figure out what is the difference between them, and then we will take the difference of times and we will figure out an average velocity. We are going now to see one example about it. But if we go to instantaneous velocity, we are trying to work in continuum, okay? So we are gonna try to pick an infinitesimal number which can be described by delta t, for example. This would be the most small fraction of time that you could imagine. It's infinitesimal, it's infinitely small, okay? So we need differential calculus. So if we want instantaneous velocity, we need dx dt. We want to figure out how the velocity is changing in a really small time frame. Okay, I don't know if I can see the chat. Okay, perfect. The same with acceleration, right? It's important to know these relations, that the velocity is the derivative of the position with respect to the time, okay? In the same way, the acceleration is the derivative of the velocity with respect to the time, but we know that the velocity is the derivative of the position with respect to time, so we can also extract the acceleration by differentiating twice the position with respect to the time. Okay? So once we understand these concepts, we can start sketching the formulations, the formulas that are going to help us to describe displacements. For example, it's very important to know that the final position of an object is related to the initial position, okay, plus the velocity, the initial velocity, which we multiply time. So these things, how do we know these things? Well, we know units, right? We know that x is measured in, let's say, meters. So in such case, x0 is going to be measured in meters. V0 is a speed, so it's meters per second. So if we want to obtain meters, we will need time, we will need seconds here. So if we multiply meters per second multiplied by seconds, we just get meters, okay? And then we want acceleration. So the unit of acceleration is meters divided by second to the power of 2, okay, squared. So we will need, in order to achieve meters, we will need to multiply by seconds squared. So that's why we reach out the conclusion that we need time squared, okay? And this half comes from differentiation, okay? Basically, this term, you will see it farther on the subject, comes from Newton, okay? Comes from the laws of, from one of the laws of Newton, which says that if you have a force, you have an acceleration. And if you have an object that doesn't have a force applied on it, that object will remain in its current state, okay? So forces are related to accelerations. That's where this comes from. This comes from Newton. This part comes from just some intuitive calculus. We know that displacement is velocity multiplied by time, and we know that we need some initial position, okay? Then we see that we have free falling bodies, but this is nothing but some acceleration, some force, right? So what force do we have? We have the force of the gravity, the force that the planet exerts on us and attracts us, right? So we have basically a vertical force, which is translated or traduced to some acceleration on the bodies. So basically we have this equation one more time with some acceleration, okay? We all know that is 9.81, you can round it to 9.8, nobody's gonna mark you bad if you say 9.8. We just try to round numbers to make everything easier, because this subject is, okay, it's important to get the right solutions, but it's more important to get the right concepts, okay? So as long as you sketch all the problem clear, it's not a big deal if you messed up with some calculation, okay? So then we see that we can have varying acceleration, okay? Where we see that there is some integral. So what is an integral? What does integrating mean? Well, integrating means averaging, averaging. Sorry if my English. It's some average. So you're trying to calculate the average of the acceleration, okay? So when you have some continuum calculus, you would integrate along the time frame that you want to study. Okay. So this is basically the summary of the last lesson. I don't know if you have any question. Otherwise, I will proceed to solve the problems that I sent you last week. Okay. Okay. If you can get written solutions for the problems, yes, you can get them. But I believe it would be more beneficial for you guys if I just solve them here in class, then you will have the recorded lesson or to watch it as many times as you want. However, if something is not clear, you can always mail me and I will forward you the solution, yeah? But I would prefer if you guys just attend or watch this tutorial at some point. So you go through the steps, okay? But yeah, okay, let's go through the solutions. Please stop me, you have any question, okay? So I believe the first question was 1.56. Let me try to find it in the... Okay, so someone suggested this one, I believe. The hydrogen mass, okay. So this is a very long, but it's pretty easy, right? If you understand what's going on. So you can use the radio waves generated by hydrogen, blah, 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 blah. So what do we need to know? The frequency of these waves, okay? So we have a huge number here, right? So they have such a high frequency. Let me erase this. Basically, the frequency is the number of oscillations per second, right? So it's the inverse of the period, okay? I also want you to know that we are not going through it now, but we will go through it, that the frequency and the period are the inverse of each other, okay? And why is that? Well, so if the frequency is the number of oscillations per second and the period is the time that you take to do one cycle, you can see the relation between both, okay? So we have the frequency. I'm not gonna put numbers, I'm gonna just put the way I would solve this problem, okay? So let's say that the frequency of the hydrogen mass is FH, okay? I'll call it FH. I don't want to write this huge number now, okay? Hertz, okay? Which is described in hertz. As definition, we know that the hertz are the number of oscillations per second. This is important, okay? So we know that hertz is something like that, right? So a clock controlled by hydrogen mass is of only 1 second in 1,000 years, in 100,000 years. We just want three significant figures. What is the time for one cycle of the radio wave? Okay, so we know that the frequency is the inverse of the period. Okay, and we just want the time, so we would take the inverse of that. Which is the inverse of that? Well, basically 1 divided by FH, seconds. Okay, this would be in seconds. So I would just do 1 divided by 1 billion, this huge number. Okay, you can take the calculator and calculate it. And you would just write 3 significant numbers, which means that after the comma, you would just take 3 decimals, okay? And how many cycles occur in 1 hour? Okay, so basically the frequency is the oscillations per second. So we would have to calculate the number of seconds that are in 1 hour. Okay, so how many cycles occur in 1 hour? So first we need to transform 1 hour to seconds. How do I transform this? Well, I know that 1 hour is 3,600 seconds, right? So 3,600 seconds is 1 hour. Okay, cross H and H, 3,600 seconds. And I know that FH is the number of oscillations in 1 second. So the total oscillations will be 3,600 multiplied by FH, right? Does this make sense? So we know that hertz is oscillation, right? So this is so now I have oscillations, right? That's why it's important to keep track on units of the units that you use, because then you know that what you do is right, okay? How many cycles would have occurred during the age of the Earth, which is estimated to be that huge number of years? So let's call H is gonna be the age of the Earth, okay? So how many cycles? Well, we would have to see how many seconds are in 1 year, and then just multiply it by the age of the Earth in years. Does this make sense, guys? It is the amount of oscillations. Oh yeah, sorry, it was completely wrong. I cannot see the chat. It was completely wrong. It's not 1 divided by seconds. It's oscillations divided by second. Yeah, definitely. Sorry, that was completely wrong. This is the definition of hertz, okay? So if you are able to remember the magnitudes of the units of every physical property, you will be able to do everything, okay? So this is a simple problem, okay? I don't know if I committed any other mistake. It's possible I commit mistakes, sorry guys. Okay, I hope this problem is now clear, okay? So we know that the frequency is oscillations per second. We know that the period is the inverse of that frequency, okay? And then we just have to transform, okay? We just have to transform quantities, okay? For example, if we have hours and we want to work out in seconds, or if we have seconds and we want to work out the oscillation, okay? So this was the first problem. If I can't solve them here, I will provide you with the solutions. I'm not gonna leave you without the solutions, guys, okay? So we now go to the problem 1.72, okay? I want to try to solve everything on time, but sorry, I have to rush a little bit, and that makes me do mistakes. Okay, we have a sailor in a small sailboat encounters shifting winds. Okay, basically this is a problem of vectorial calculus, right? So let's see. Okay, let's start by the fact that we have a displacement of 2 kilometers in the x direction. Then we have another displacement, 45 degrees. This is important. Which magnitude is 3.5 kilometers, okay? And then we have a third displacement, which we don't know anything about it. However, we know the final position, which is 5.8 kilometers. Okay, wonderful. Okay, so basically, we want to work out. First of all, it would be helpful if we can work out the components of the second vector, okay? I don't know if I can see the chat, if anyone. Okay, wonderful. Okay, so basically, what we are gonna do now is, first of all, let's call this vector A. I'll call the second vector B, the second displacement vector B, and the third one C. Okay, the one that we want to figure out. And we know that this 5.8 kilometers could be another vector, displacement vector, that could be just 5.8x. I'm gonna work out with the notation of I plus J, okay, two-dimensional. So first of all, we know that this is 45 degrees, which means that the Y, the I and the J components are gonna be equal. Does this make sense? So basically, in B, I know that AI plus BJ. Okay, I know this is negative, but B can be negative, a negative quantity, right? And I know that A is equal to minus B, because in my reference system, I'm gonna consider positive upwards, negative downwards, okay? This is another important thing that you have to keep in mind, that you have to be consistent, okay? So let's say this is X positive, this is Y positive, okay? So those two quantities have to be the same. And I also know the magnitude, which is 3.5. So I know that the magnitude of B is 3.5 kilometers, 3.5, okay? If there is any question, okay. So I just have to calculate the magnitude. How do I calculate this? Well, basically, I can do like some Pythagorean theorem, right? And then I can infer the components of the vector, if this makes sense, okay? So I know the magnitude, I know the angle, I can obtain. What else do I know? Okay, now I know that the summation of all these three vectors is gonna give me this vector, which means that A plus B plus C. So I'll call this vector D. It's gonna give me D. I know that D is 5.8 I plus 0J. You don't have to write this, I just write it to let you know that J is 0. You can write J 0, or you can leave it like this. It's perfectly fine. So we know that A is equal to 2I. We know what B is equal to once we obtain A and B from this equation. Okay, because, well, from this system of equations, because we have one and two equations with two unknowns, we always need to have the same unknowns than equations, right? Otherwise, we can, in this subject, you're gonna always have the same equations than unknowns, okay? And yeah, I believe with that you can obtain C. Don't know if it's completely clear this or not. We barely have time, but yeah. Hopefully it's clear, guys. I don't know. Send me any question. Okay, so I'll skip. Okay, wonderful. Let's go to the third problem that we had. Okay. So it's 1.73, blah, blah, blah. This dislocated shoulder, a patient with dislocated shoulder. Okay, this is really easy because we have symmetry, okay? And symmetry is important. It's gonna give us some clues. So basically we have 32 degrees and 32 degrees. Okay, and we have, let's say, A and B. A and B. Okay. What else do we know? Okay, we want an outward traction force of 5.6 newtons. So let's call it T. And we want a T of 5.6 newtons in the direction of X, okay? So what does this mean? Well, the first thing that we can notice is that T doesn't have an Y component, okay? We have, as always, Y and X positive, okay? Y positive, X positive. So it doesn't have J, which means that, okay, let's say A is equal to A and B is equal to some components. A, we don't know A and B yet, and we don't know C and D yet, okay? Okay, A and B. What do we know? Well, we know something about the J components. We know that they must be equal, okay? So B is gonna be is equal to D, but they have different directions, okay? So B is gonna be equal to minus D. Okay, so which means that B plus D is equal to 0. Okay, so we can leave it like that because it actually doesn't oh well, it matters because we are giving an angle. Okay, sorry. So 32 degrees. Okay, what else do we want to know? Okay, we want to know the product of them. Okay, what do we know about it? Well, let me have a look. We can also try to infer it by trigonometry, right? If you know the trigonometric relations and you know the angles, you can figure out everything, right? Because this is 32 degrees, so we know that the cosine of this, the cosine of 32 degrees is equal to, I'm gonna call this, let's say, R, okay? I'm gonna call this R, and I'm gonna call this Y, and I'm gonna call this X, okay? So we know that X divided by R, sorry, is there any problem? Okay, no, there is no problem, sorry. So by trigonometry, we can work out the components, okay? So we can build a system of equations with trigonometry and with this, okay? We also know that the sine of 32 degrees is gonna be equal to Y divided by R. And we know the same about this one, okay? So basically we have 1, 2 equations, 3 equations with 3 unknowns, okay? Oh, okay, fair enough. We also know something else. We know that we want 5.6 in the direction of X, right? So we know that something about A and C. What do we know? We know that A plus C is equal to 5.6. And we know that they work in the same direction, okay? So newtons. So A, or do we know they are equal as well? So we know that A is gonna be equal to 5.6 halves and C the same. Does this make sense? Does this make sense? This is a very intuitive problem. Okay, wonderful. I'm surrounded by clever people. That's really nice. Okay, guys, I'm going to sketch the last one very quick because I already exceeded the time. I'm sorry for stealing your time. but I have an option if I want to give you the solutions. It is not the solutions, but it's the most important part and it's the way to solve the exercises. Okay, and it's the exercise 1.95. I'm really sorry for taking your time. Okay, you're given two vectors and you have to obtain a third vector. You know some relations amongst them, okay? So you are given A and B. You know A, you know B. I think this problem is quite tricky, and if you achieve to solve it, you are doing amazingly well, okay? Because this problem encloses a lot of the chapter, okay? We know A and B, so I think one really nice way to approach these problems is to make a small sketch for yourself so you understand what's going on, right? So you can basically draw the frame, let's say X positive, Y positive, okay? And you can work out that more or less, okay? I'm not gonna spend much time on how to draw vectors. I think you already know how to. A is gonna describe something like that, okay? It's maybe it's not perfect, but and B is gonna be something like this. Okay, I hope we all agree. If we looked at the, we know that is equal to 5i. Oh no, no, it's negative. A is negative, sorry. Okay, so A is 5i minus 6.5j. So it's gonna be something like this. And B is equal to minus 3.5i plus 7j. So we know it's negative in the direction of x and positive in the direction of j. Okay. What else do we know? Well, we know that the third vector C lies in the xy plane. Well, we know that all of them lie in that plane because they only have I and j components. So we know all vectors lie on the xy plane, okay? Vector C is perpendicular to vector A. So we have A, and basically we're gonna draw a perpendicular line. So C is gonna be either pointing here or either pointing here, okay? It's gonna be on that line, more or less, okay? And also we know that C, the scalar product B, is equal to 15. Okay, this is a really important information because this is also gonna give us the direction of C. Why? Because this is positive, and whenever the scalar product is positive, it means that the angle is less than 95. And why is this? Well, because C scalar product B is function of the sine, no, of the cosine, sorry. So we know that is C B cosine of the angle that they describe, and the cosine from 0 to 90 is positive. Well, the cosine of 0 is 0, right? No, it's 1. The cosine of 0 is 1 and the cosine of 90 is 0, okay? But everything else is positive, and the cosine from 90 to 180 is negative, okay? So we know that this is smaller than 90. We know that C is gonna be in this direction, okay? So more or less we now know how C is gonna look like, okay? Okay, what else do we know? Okay, so we also want to figure out what is the angle that B and A describe, okay? So how do you figure out the angle that two vectors describe? Well, you have properties like, for example, let's call it alpha. You know that the cosine of alpha is gonna be related to the magnitudes and to the vectors themselves, okay? So it's gonna be the scalar product of them divided by the magnitudes, the product of the magnitudes. Okay, What else do we know? Because we need more information, okay? It's 15. Okay, you know that they are perpendicular. So C is perpendicular to vector A. Okay, so once we know alpha, if we subtract 90 degrees from alpha, we will be able to obtain the angle that C and B describe. Okay, let's call it. So we have, because we know they are perpendicular. Does this make sense, guys? I'm sorry if I'm going really fast. I will provide you some solutions for these exercises because this is really fast, okay? So basically we can figure out the angle that A and B describe. We can figure out the direction of C more or less by intuition. We can also subtract one angle to the other because we know A and C describe 90 degrees. So we can infer the angle between C and B. And what do we do with the angle between C and B? Well, we know that C scalar product with B is 15. So we can build up some equations from here. Okay, so we have that. And yeah, that should be most of it. Anyway, I will provide you with the solutions, guys. And hopefully next time we will have more time to go a bit more deeper on this. So is it clear? How do we solve this problem? Does anyone encounter any problem with this or? Okay, I'll provide you with the solutions this time, but it's likely that next times I'm not gonna provide you with the solutions. I prefer if we can solve them all together, okay? And we can have a little bit of interaction. So I believe this is everything for today, guys. You will receive tomorrow the solutions for these problems and the suggested problems for the next week, okay? So good luck with everything. And let me know if you encounter any problem. Feel free to contact me, okay, guys? So have a nice day and good luck with everything. Sorry, where can we find the next problems, by the way? Okay, the next problems, I will upload them to the Learning Central, okay? No, you are not meant to submit them, just to attempt them, just for your own benefit, to improve. Okay, guys, have a nice day. That's everything. I will mail you with everything. And if you can't see the mail, just go to Learning Central. You will find everything there, okay? Solutions and the next problems. Have a nice week, everybody. Bye.